welcome Amanda Giang to back to U of T. So Amanda did her undergraduate here several decades ago. She finished in 2011, did her our engineering science degree in the biomed. And I remember talking with Amanda because I tried to convince her to do her graduate studies here with my group. But she's very, very bright. And she really wanted to do policy, and I don't know which of those two it was that convinced her to go down to MIT. So she's one of the, really, we've had a slew of students who've gone down. We're talking about Paul and William. There's been a bunch of people who've gone down to MIT. And generally, if people want to do policy work, Carnegie Mellon and MIT are the two programs that really stand out for this sort of work. So when the opportunity came, because of the award you got in the S&T, I saw that. I go, I know that person. Well, I'll read that paper. Amanda got an award for one of the top papers in environmental science and technology last year, and I thought, what a great excuse to invite her back. And I thought it would make such an incredible presentation, up the pressure on you now, that, and since I know you love to come back to Toronto, see family, that sort of thing, so I thought it would be great to have you come back to the SOCAAR Seminar. So we're so happy to have you here, and join me in welcoming Amanda.
Thank you so much, Greg and SOCAAR, for inviting me. It is such a pleasure to be here, to be able to come back to Toronto. And I'd also like to take this opportunity to acknowledge that this land that we're gathering on has been the traditional land of the Huron-Wendat and the Seneca, and most recently the Mississaugas of the Credit River. And this meeting place today is still the home to many Indigenous peoples from across Turtle Island, and I'm really, really grateful to have the opportunity to be here today with you here. Currently, I'm a PhD candidate in the Institute for Data Systems and Society at MIT, and I'm also affiliated with the Joint Program on Science and Policy of Global Change. And my research focuses on assessing the impacts of mercury pollution for human exposure using modeling and qualitative social science approaches. And so really excited to be able to be here with you today to try to start this dialogue about broader issues and connecting air quality science and policy, and hopefully we can keep this fairly informal. So, if you have a short question or clarification, feel free to, just ask. Okay, so to start, I wanted to go over briefly why we care about mercury, key exposure pathways and impacts, and the punchline is that mercury poses risks for human and ecosystem health. And while mercury is a naturally occurring substance, much like with carbon, human activity extracts mercury from deep terrestrial reservoirs, and it increases its mobilization in air, water, and soil. And this human activity includes mining and the production of metals, including not only mercury itself, but also gold, iron, and zinc, where mercury is released as a byproduct of the ore. Combustion of coal, again, where mercury is an impurity and gets released upon combustion. And then several other industrial processes where mercury is used intentionally. And then these emissions, once emitted, can be transported atmospherically, and they can travel short or long distances depending on chemical form. Mercury in its elemental form actually has a fairly long lifetime in the atmosphere, 6 months to a year, while in its divalent form it's closer to days to weeks. And so once this atmospheric mercury is deposited into aquatic and terrestrial ecosystems, it can be transformed into methyl mercury, and this is the particularly toxic and bioaccumulative form which bioaccumulates with fish. And then this process can really depend on the ecosystem, whether it's marine or freshwater, for instance. And then in the US, Canada, and elsewhere, fish consumption is the primary exposure pathway for most populations. And because we exist in a globalized economy, you can get your fish locally, or that fish might come from a very distant ocean basin. And so if we want to understand human exposure, we really need to think about what fish people are eating and where that fish comes from. Mercury may have a wide range of health effects, even at chronic low to medium doses, and the most clearly elucidated ones are neurodevelopmental effects from in utero exposure, but there's also growing bodies of literature that point towards cardiovascular and immunologic effects. And then moreover, mercury contamination can pose risks to cultural, spiritual, and social dimensions of well-being. And then these impacts to health and well-being at individual or community levels can also have wider socioeconomic effects. And so mercury traces this complex path from emissions to impacts, crossing space, crossing time, and it poses these risks to human health and well-being and economic welfare. And so because of these risks, mercury has been the target of policy at various spatial scales. So for instance, in Canada, policies targeting key emission sources like metals production have really dramatically reduced emissions since the 1990s. And what's more, a recent UN Global Environmental Treaty targets mercury, the Minamata Convention. And this was adopted in 2013, and it's likely to come into force next year. So basically, we're expecting to see hopefully, some major shifts in mercury emissions on a global scale. And so given these events, a question that motivates my work is, what are the potential impacts of global and regional mercury policy for exposure for populations in the US? And in this talk, I'm going to try to highlight some implications that this work has in terms of policy design and policy evaluation. So I'll be discussing 3 chunks of work that address the following questions. First, how might policies targeting mercury pollution change emissions? 2, what are the potential human health and economic impacts of these policies and their associated emissions changes for populations in the US? And then finally, can we detect these projected changes? Can we use existing environmental monitoring networks to verify that these policies are having the impacts that we hope that they do? So, onto the first part. This section draws from 2 papers, one in ES&T and one in Global Environmental Politics. And I want to quickly acknowledge my coworkers, my collaborators in this work, Leah Stokes at UC Santa Barbara, David Streets at Argonne National Lab, Bess Corbett at Harvard, and my advisor, Noel Fleet. So, like I mentioned, we have this new global treaty for mercury. It's very exciting, the Minamata Convention, and it addresses a lot of mercury's emission sources, about 96% of them, importantly including artisanal and small-scale gold mining, coal combustion, metal smelting. It was adopted in 2013, and currently it has 128 signatories. Canada is one of those signatories, and 32 parties. So Canada is still in the process of ratifying that treaty domestically, but hopefully will become a party soon. Also important are that signatories include China and India, and I mentioned those 2 countries as important because they're 2 leading mercury emitters. Asia currently contributes 50% of global anthropogenic mercury emissions, and that share is growing over time. So what does this treaty actually mean in terms of emissions? Well, what the treaty actually calls for is for parties to control and, where feasible, reduce emissions through things like best available technology and best environmental practices, quantified goals, emission limits, multi-pollutant control strategies, alternative measures to reduce emissions. And so what you might notice is that the language is a little squishy, it's a little bit vague, and if you're familiar with global environmental treaties, that's not surprising because it's really hard to get people to agree on things, and so a little bit of ambiguity is helpful just to grease those cogs. And so, but moving forward, then what do we make of this, right? What does best mean? Does best mean best on the market? What does available mean? Does available take into account socioeconomic development or technological capacity? And that was a question that we wanted to explore a little further and dig into. And we thought a good way to do this would be actually to combine different sorts of methods. So in this work, we used some qualitative methods. We collected data through participant observation during the negotiations themselves. We did interviews with delegates at the negotiations, regulators, and experts in major emitter countries. And then we also followed up with quantitative analysis of air pollution control technologies and techniques and their potential impacts on emissions. So based on these data sources, we developed some representative technology scenarios that capture different ways that the treaty could be implemented in China and India. The first scenario represents no additional control. So what are the sorts of things that are already happening in these countries? Then we have what we're calling our flexible best available technology scenario, and then we have a more stringent scenario. So this chart shows projected emissions from coal combustion in 2050 under the 3 different technology scenarios I mentioned. And China is in blue and India is in red. And then the different shades of blue and red represent those different chemical forms of mercury that I mentioned that have important implications for transport. So for China, recently there's been a lot of public pressure on the topic of urban air quality, and it's really forced the government to respond to this through regulation. And this is relevant because for mercury, there can be a lot of co-benefits in terms of trying to capture and control traditional air pollutants like SOx, NOx, and particulates. You can also capture mercury as a side benefit. And so China has been issuing new emission standards for these pollutants. And so from China's perspective, they're really interested in getting some of these mercury emissions reductions for free, just as a byproduct of their approach to addressing these urban air quality issues. And so if we define best available technology in a flexible enough way that also includes the sort of multi-pollutant approach, then China's actually in a very good place. And there's we project an emissions reduction of 91 megagrams for 2050. But if China were to take one step further and then use more mercury-specific techniques, there are some additional gains possible. But you'll notice that the bulk of the potential reductions actually can be achieved with traditional air pollution control. So in India, we have a very different narrative, a very different set of domestic regulatory politics. There's substantially less mobilization around the issue of air pollution, particularly from stationary sources in India than in China. And part of that has to do with the fact that energy access is still a real issue. The government is still focusing on trying to provide electricity to all of its citizens. And so ramping up electricity generating capacity in the next couple of decades is a priority. And India sits on a really large domestic coal resource, and it would like to use some of that coal resource to address these energy access needs. But another reason that air pollution from stationary sources like power plants has been a less salient issue in India also has to do with the nature of this coal resource. So Indian coal actually tends to be relatively low sulfur, and so historically, while Indian power plants do have to control for particulate matter, SOx controls haven't actually been seen as necessary, and so it's less you have less opportunities to get that sort of co-benefit win-win approach. And so from an Indian perspective, using flue gas desulfurization is kind of mercury specific because they're not as interested in the SOx control. And so instead, India is much more interested in pursuing an energy efficiency angle, which is also seen as a triple win, right? More energy access, you reduce emissions of pollutants like mercury, and then also you reduce your emissions of greenhouse gases. But if India were to adopt some of these more traditional air pollutant control technologies, the additional gains could be quite substantial. So something else we wanted to consider, though, was what these different technology scenarios might look like under different assumptions about energy and development. So the underlying assumptions about energy and industrial activity come from David Street's group at Argonne National Lab. And on the left, we have a scenario that has continued reliance on fossil fuels, particularly in emerging economies. And then on the right, we have a scenario that involves deeper decarbonization, and so shifting away from fossil fuels. And so what's interesting here is that even if we don't change the sorts of end-of-pipe technologies we're using, but we do shift away from fossil fuels, you see very comparable, if not larger, reductions in emissions. And so and this is even more apparent if you also consider emissions from other sectors other than just combustion. And so there are a couple of, I think, policy-relevant insights from this work. The first is just the importance of considering co-benefits from other environmental domains, right? Shifting from single pollutant approaches to multi-pollutant approaches and thinking about where there might be synergies. And then also thinking beyond just end-of-pipe controls, which is something that can sometimes happen when we're talking about air quality, just put a scrubber on it, to thinking about broader energy transformations. Another important insight for policy design, though, is trying to understand these factors that contribute to variability in implementation of policy. Sometimes, when we're trying to do policy assessment, we treat policy, as if it lays out this strict trajectory of emissions. And in reality, that's very seldom the case, right? And especially at the global level, more often we have language that says things like, try to reduce, alternative measures to, and understanding what that actually means in different countries is an important part of trying to understand what the impacts of those policies will be. So the next area of work I want to talk about looks at what these sorts of emissions reductions we just talked about might mean for populations in the US. And this is drawing from a paper we published earlier this year. And so we wanted to ask, what does global policy mean for the US? And so we wanted to look at the Minamata Convention. But as a useful point of comparison, we also wanted to look at US regulation. And so the US had recently come out with a standard, the Mercury and Air Toxic Standards, or MATS. And the interesting thing about MATS is that in the process of writing this paper, MATS came under legal challenge, which is probably a comment on how long it takes to write papers. So for all the graduate students out there, you want to write your paper and have it out before the policies change. And anyway, so MATS came under legal challenge. And these challenges actually had a lot to do with the question of what the monetized benefits of these policies are. And so this is a New York Times article. It says, so the Supreme Court blocks Obama's limits on power plants. And so Justice Scalia, who wrote the majority opinion, wrote, it is not rational, never mind appropriate, to impose billions of dollars in economic costs in return for a few dollars in health and environmental benefits. Statutory context supports this reading. But later on in the same article, it says the two sides had very different understandings of the costs and benefits. Industry groups said the government had imposed annual costs of $9.6 billion to achieve about $6 million in benefits, and the agency said the cost yielded tens of billions of dollars in benefits. So I highlight this article for two reasons. One is to say that in this paper we focus on quantifying impacts and benefits in dollar terms if we monetize them. That's not because it's the only or most important way to think about impacts or benefits. But it is a way that has a lot of cachet, particularly in U.S. regulatory discourse, where here in this case you can see that the perceived discrepancy in those costs and benefits really opened up this regulation to legal challenge. The other reason I bring up this article, though, is that it also highlights, the huge range of estimates that we can have in benefits. And so in this paper, we're also trying to understand what factors contribute to these very different understandings of what those benefits might be. So to do this, we developed an integrated assessment approach to try to trace through from emissions through to impacts. And necessarily, because we're trying to trace from emissions to impacts, it's very much a first cut approach. We had to make a lot of simplifications. But we thought it would still be valuable to try to synthesize across this chain to try to explore some of those questions of how to upstream uncertainties affect those downstream benefits estimates. And so I'm not going to go into a lot of detail, but if you have questions, please ask me, after, in the question section. But I just wanted to highlight some of the different kinds of modeling that we tried to incorporate. So we started with this question of emissions to deposition. And for that, we use the GeoChem chemical transport model. So this is a global chemical transport model it's driven by assimilated meteorology from NASA GEOS. And in this paper, we were modeling globally at 4 by 5 degrees and at a finer scale over North America at 1/2 by 2/3 of a degree. It's a Eulerian model. The next step in the process is how do we go from this spatial pattern of deposition to understanding U.S. exposure? And here we were drawing on work from ecosystem dynamics of mercury and then also papers on the global seafood market, U.S. dietary choices, and some baseline epidemiology studies. Once you figure out how much mercury people are getting as dietary intake, the next question is, what are the health impacts of that? And we were drawing on a wide range of epidemiological evidence addressing mercury's effects on IQ and then also on heart attack risk. And then finally, to value these health endpoints, these physical health endpoints, we use two different approaches. One is a computable general equilibrium approach, and the other uses value of statistical life and cost of illness. And I'll explain some of these in a little more detail later. And in the interest of time, I'm just going to focus on results from this last part, the valuation part. But again, I'm happy to talk about the other parts and questions. So I mentioned that we use two different valuation approaches, but for this talk, I'm just going to focus on one of them, because this is the one that's most commonly used in regulatory impact analysis. And in this chart, we're showing projected yearly economic benefits from reduced incidence of IQ and cardiovascular effects per year. In the green line, we have the projections for the Minamata Convention, and in the purple for MATS. And what we're counting as benefits here are the projected lifetime benefits as avoided lost wages and medical costs, willingness to pay for reductions in fatal heart attack risk for individuals who would be affected in any given year. And so in our simulations, by 2050, the cumulative benefits of global action we estimated to be more than twice that of domestic action, at $339 billion against $147 billion. But we wanted to understand what some factors might be that contribute to variability. So we did some sensitivity analysis using policy-relevant high and low assumptions for different drivers of uncertainty in this path from emissions to impacts. And so these different, the lighter lines show the results from that sensitivity analysis. And so another way to look at that sensitivity analysis is just looking at those the cumulative number. And so this graph shows the selection of those critical uncertainties along this emissions to impacts chain that we were considering. And then how high and low case assumptions for each of these affects the range of benefit estimates. And so the line in the center is that base case estimate that I showed in the last slide. And so this is just for the Minamata Convention. And so from this analysis, I think there are a couple of interesting things to note. The first is that dose response parameterization, this question of intake or exposure to health effect, is a huge source of uncertainty. And traditionally, when people think about uncertainty in benefits, this is the part that they focus on. And our analysis really supports that because when you think about that huge range that the New York Times article was citing, a huge part of that does have to do with dose response. And a large part of that also has to do with variability, right? The fact that different people are going to respond differently to different sorts of environmental stressors. So to a certain extent, part of that uncertainty is that it's difficult to estimate these relationships in epidemiological studies. It can be difficult statistically speaking. And then part of it also has to do with the fact that there is some natural variability and people will respond differently depending. But we think that this analysis also highlights a couple of other critical uncertainties. One of those is time lag, so that's the time it takes for changes in deposition to be reflected in fish tissue concentration. And there's a huge amount of variability there because ecosystems, different watershed systems are very different. Another one is fish source, so dietary fish, whether people are eating local or global fish. And these two sources of uncertainty are less often taken into account. These kind of more upstream environmental uncertainties aren't necessarily always taken into account in this sort of policy analysis. So, actually, I just want to highlight one more thing about the dietary fish source point. In most of these different sensitivity cases we were considering, the finding that global policy contributes more benefits to the U.S. than domestic policy was quite robust. But the one exception is this question of fish source. If you're eating predominantly locally caught fish, then domestic action remains really, really important. And so in terms of policy takeaways, I think that is a key one to make, right? That the global policy is really important for U.S. benefits in aggregate. And that means that the U.S. should aggressively be pursuing the Minamata Convention and supporting other countries in pursuing the Minamata Convention because it stands to gain a lot from that. But it can't just do that alone because domestic action is so critical for protecting sensitive populations that eat local freshwater fish. And there are a lot of communities that eat a lot of local freshwater fish for subsistence, spiritual, cultural, recreational reasons and eat a lot of that fish, right? So a lot of these are very vulnerable populations for mercury. And so both the global and the domestic policies are necessary. The second point, though, is that these monetized benefits estimates are quite sensitive to these different sources of uncertainty. And so, one, it points to some key areas of future study. These are uncertainties that we'd like to better constrain to better understand these benefits. And it also makes us think about how we take these uncertainties into account in this sort of regulatory cost-benefit analysis. The way things are often done is that if something is difficult to quantify, it just won't be quantified, and they'll discuss it qualitatively because they, regulatory agencies might feel that they don't have, the expertise or the data really to do some sort of quantification on that. The challenge comes then with how people use the results of that analysis, and often people focus just on monetized benefits, and so. How do we weigh, benefits that are easier to quantify, that have less uncertainty, against ones that are more uncertain but potentially really important? So, okay, now I want to turn to the last chapter. So in the last chapter, we projected these benefits. It's great. We hope that they're going to happen. And as we move forward and implement these policies, how do we know that they're working? And so this is ongoing work I'm doing right now with my colleague Xiaoji Song at Harvard, Marilena Muntien, who works at EDGAR in the European Commission, Abby Harvey and Elizabeth Berg, two lovely undergraduate research assistants who have been working with me, and then my advisor. So this question of will policies actually translate into changes in environmental loadings is one that we've heard from our community partners in the Laurentian Great Lakes region. The Great Lakes is an area that's vulnerable to mercury pollution, both because it receives a fairly large amount of it, and also because it's home to a lot of communities that depend on fish for subsistence, spiritual, cultural, or recreational reasons. And so for these affected communities, in our discussions with these stakeholder groups, their concern is that it's great to have a policy in place, but what we really care about is actual environmental improvement. Our question is, when will the fish be safe to eat? But this question is also relevant to a lot of policymakers who are interested in issues like compliance and evaluation, right? Are people actually following the rules? And do we need to reevaluate these rules? So one thing we can do is look in historical data. So historically, if we look at what's happened in terms of emissions in the US and in Canada, we see really large decreases, right? So, you know, in the US, particularly policies targeting waste incineration, and in Canada, oh sorry, I didn't label this correctly. The left is the US and the right is Canada. In Canada, metals production used to be a very large contributor to mercury emissions. Those have decreased quite dramatically. Even in the past 10 years, we have seen emissions reductions of close to 50% in both these countries. So what does this mean? What does the monitoring data say? So we looked at observed trends in mercury wet deposition. There is a wet deposition monitoring network both in Canada and the US. And we wanted to see whether we saw a trend in the wet deposition data. And so in this plot, I've shown sites of these different monitoring stations with continuous data from 2005 to 2014. And for each site, we show 3 boxes. The top one is deposition, then concentration, and then precipitation. The color of the box shows that trend as percent per year, and we calculated that using the seasonal Mann-Kendall trend test and Sen's estimator of slope, which would be a non-parametric equivalent of doing a linear regression that's taking into account seasonality. And then where we found significant trends, we indicate that with a dot. So, you know, when we look at this, there are actually very few sites that have significant trends in concentration or deposition, and some of those trends are actually positive. So how do we make sense of that finding then? Is what we're seeing here consistent with those sorts of emissions decreases that I showed on the previous slide? And if so, what does that mean for what we should expect under future policies? And, you know, there are a lot of different hypotheses we might have as to why there is that mismatch, right? You know, it could be that the emissions inventories are wrong. It could be that there's a lot of variability in those emissions that we're not taking into account. Maybe emissions in US and Canada are decreasing, but they're increasing everywhere else. And, you know, maybe there have been changes in rainfall pattern that also affect deposition. And so this is where, you know, modeling seems like a really useful approach, because we can't run experiments on the Earth like this using our modeled system. We can explore some of these what-if scenarios and try to develop some process-based hypotheses about what's going on. And so specifically what we want to investigate here is, given the noisiness of the system between policy and environmental loading, so, you know, the fact that there will be variability and there will be trends in some of these intervening factors, under what conditions could we detect this policy signal? So again, we're using the GeoChem model to do this experiment. Here are some model observation plots. And in our experiment, we use these stylized policy scenarios based on the sorts of policies I just discussed, MATS and the Minamata Convention. And we treat the policy as a step change between a pre-policy period and a post-policy period. And so what we're going to think of as the policy signal is the difference between the pre-policy and the post-policy period. And so we looked at both, you know, regional signal, regional policy for North America, and then also a global signal in terms of the rest of the world. And holding everything else constant, if all that's changing in the world is just, you know, changing that sort of technology leading to emissions decreases, these are the sorts of emissions decreases we could expect. So for North America, it'd be about a 30% decrease in emissions. For the world, it would only be about 13% decrease, but in magnitude it's much larger. There are a lot more emissions in the rest of the world, so that's about 6 times as large as the North American policy. And so, again, we were thinking about this policy signal as the difference between the pre- and post-policy period. And so in this plot, we're showing the colors represent that pre-post policy difference represented as a percent change. And the triangles show the locations of those monitoring sites. And then wherever there's a significant trend detected from that grid cell, we put a dot there. And so, and the way that we use, the technique we use to do that is basically a non-parametric equivalent to doing a t-test in a different circumstance. And the first thing you'll probably notice then is that if all that's changing is that policy, is those emissions, holding everything else constant, then you should see a negative trend everywhere, and all of those trends should be significant. And what's more, you'll see that in terms of the North American versus the global signal, the magnitudes are quite similar in the region, about 4 to 5%, but there are differences in the spatial pattern, right? And in terms of the regional signal, you see a pattern that much more reflects the locations of local or regional emission sources, whereas the global signal represents changes to the global background concentration of mercury. So what happens if we introduce some noise? And we looked at a couple of different factors, but I'm just going to focus on 2 for this talk. It showed in the previous slide that the signal for these policies, holding everything else constant, is at about 4 to 5%. So then what happens if we introduce some variability into the performance of the control technologies I mentioned? So we'll consider the same mean for the pre and post policy period, but now we're going to draw from a distribution of the performance parameterized based on measurement data. And for the most part, these distributions are fairly tight. They're not, if we have a mean of 80% capture, in terms of 2 standard deviations might only take you to 87 and then 93. So a relatively small amount of variability. Just introducing that already really dampens that sort of policy signal, right? We see a decrease in, pretty large decrease in the strength of the signal, and even though all sites still show a significant signal. Next, though, we wanted to look at interannual variability in meteorology. And so instead of holding meteorology constant, now we're using historical meteorological data in the pre and post policy period. And so now, looking across the sites, we actually see a sign change and a really dramatic drop in the number of monitoring sites that show any sort of significant trend. And so if we look at this spatially, we see a much more heterogeneous spatial pattern. There are areas where we see trends increasing. And the similarity between the North American and the global picture suggests that these changes are likely driven by changes to precipitation rather than meteorological changes that affect long-range transport. And so this pattern actually looks a lot closer to the observed trends that we saw earlier, suggesting that these year-to-year changes in meteorology may play a really dominant role in what we observe. You'll also notice that there aren't a lot of monitoring sites located in some of the areas that we predict could be seeing significant trends. So there are very few monitoring sites in Ontario, right? Active monitoring sites currently in Ontario. So in terms of thinking about what this might mean for policy, it suggests that we really need to think about the envelope of possible impacts that could be consistent with policy action, in particular, given factors like climate variability and change, when we're thinking about policy design, right? Because, we might see no change in environmental concentrations, for instance, and that doesn't mean that emissions aren't decreasing. But that does mean maybe that we need much more aggressive decreases in emissions if we want to see something. And it also, brings up these questions of time of emergence. So how long, for instance, would it take for us to see a policy signal of a certain size, given the strength of this noise? Or alternatively, how large of an emissions decrease would you need to see to not be swamped out by this sort of noise in the short term? And so in ongoing work, we are trying to do a better job of quantifying that, focusing on this idea of focusing on the meteorological variability piece. And we're working with colleagues at the joint program at MIT using an ensemble of global climate model results so that we can look at things like internal climate variability and try to quantify the extent of that sort of noise. So in terms of monitoring network and design, though, I think these results also highlight monitoring network design as a pretty important policy challenge for environmental policy. Especially as we focus a lot often just on getting the environmental policy, and we know that in and of itself is a huge challenge. But moving on from there, once we start implementing policies, particularly those with cross-scale effects, we need to think about whether or not we can see those changes and what we need to do to be able to monitor for compliance and for evaluation. And so, we have to think about whether or not we need to change how we're monitoring or where we're monitoring in order to see policy changes. Because often, that doesn't necessarily always match up with our scientific monitoring goals, right? There are certain sites that are valuable for monitoring from a scientific perspective, but might not speak as well to understanding or seeing these policy changes. So I think those are some interesting areas for future work. And to conclude, I just want to reiterate some of the cross-cutting themes from across some of these different chapters. The first is that, these sorts of uncertainties and variabilities I talked about in these different social, technological, and natural systems are things that we need to take into account in policy design and evaluation. and thinking about what are different ways we can confront those sorts of deep uncertainties. And, especially from an engineering perspective, something we think about often is, well, can we better quantify, can we better characterize that uncertainty? That's certainly an area I think there's a lot of exciting work on, thinking about what are the approaches we can use to characterize different kinds of uncertainties, different levels of uncertainties. There are some uncertainties that, make sense to put a probability distribution around, and then there are some where it doesn't, and maybe that's the case where we want to use scenario analysis. For those of you who do environmental or atmospheric modeling in particular, you'll know that probabilistic approaches can be a challenge given the sorts of computational needs for air quality modeling. So innovations in terms of reduced form modeling or other ways to be able to use a probabilistic approach, I think is a really interesting area of future work. Another way, though, that we can think about confronting uncertainty has to do with adaptivity, right? We might just have to come to terms with the fact that there are some uncertainties that are irreducible, or at least irreducible in the short term, right? And yet we still need to move on and continue and do things. So how do we develop a learning approach? How do we develop systems where we can continue to collect data, continue to try to see what these effects are, and have opportunities to change policies or change our approaches? And so, you do see a lot of adaptive management approaches in things like fisheries management often, or forestry. Thinking about, how we might do that for a plume like mercury would be interesting as well. And then finally, I mentioned this idea of participatory approaches as another way of confronting these uncertainties. And earlier I was at lunch with Jen Murphy and Miriam Diamond, and we were talking a little bit about this idea of, what does doing more participatory or community-involved work in this area look like? And in this case, it's the idea that, there are these deep uncertainties, and some of them aren't going to have a technical solution or a technocratic answer. Some of dealing with these uncertainties involves making value judgments about how we proceed in the face of uncertainty. And if you're familiar with the precautionary principle, you can see that as, in some ways, a value-based judgment over what we do under uncertainty. And so, also thinking about different sorts of approaches to bring in more deliberation, democratic deliberation. And this idea of an analytic deliberative model. In environmental policy, we need strong analysis, but we also need deliberation. So how do we bring those two things together? And then finally, I think this work also highlights the idea that we have to think about shifting from individual policy instruments to an entire policy ecosystem or a governance landscape. Thinking about where there might be co-benefits and where there might be trade-offs, for instance. And I think this opens up a lot of interesting questions about coordination across different sorts of policy domains and integration. And I think an interesting area of work that people are working on in terms of air quality stuff is thinking about synergistic effects, or trying to co-quantify pollution and think about what those cumulative and synergistic impacts might be. So with that, I'll conclude, and I just want to quickly acknowledge again my advisor, my collaborators. I think I mentioned most of my co-authors, but I also wanted to mention I'm part of a larger U.S. National Science Foundation project based out of Michigan Tech, and so I also wanted to mention my colleagues at Michigan Tech, the Desert Research Institute in Nevada, and the Northwest Indian College, and then also all these generous funding sources. And yeah, with that, I will take your questions.